into chat. All right, successfully added to that. Okay, so the idea of let's just go over what we have, because I reset where we are from yesterday. So all of the like code that I added in, I ripped that out because I want to start from scratch with this. Because I discovered in sort of like playing around with this last night that I came really close to implementing it properly. But I sort of like implemented several different solutions, and also one of them was completely wrong, which is why we didn't see any like advancement from it, which started us going down the wrong path. Let me move the microphone a little bit closer. All right, and the T goes there. So the first thing is, let's just sort of like run the game and see where we are with it. If we do cargo run, we get about, what is this? 200, 220 frames per second. And the frames are like wildly different. They're all over the place. And that's because the loop is running as fast as it possibly can. And so when we start adding in a lot of these other things to draw and add on to the screen, that affects how fast we can loop through the game. On top of that, if I run my task manager, I could see that, where is it? Here it is. The GGEZ Infinite Runner. This is using 6.5% of CPU, 39 megabytes of memory. That's not really going to change from this. But 9.4% of the GPU based upon what we have right now. Okay, and very high power usage. Okay, that's fine. Let's go ahead and run this in release mode and see what we get. The game is unplayable. It plays significantly faster. We're getting 2,500 frames per second or so. And if we take a look at what we've got here, it's now 11.9% CPU, same amount of memory, and around 70% GPU. And also, of course, once again, very high power usage. So that's what we want to solve. We want to basically have the game play the same speed, as it were, regardless if we're, what their frame rate really is. So let's implement that first. What that means is coming into our main library. We want to get to update here. Where is our update? Let's go ahead and fold everything. How did I switch? Okay. My keyboard switched somehow. Okay. Stay in here. There we go. All right. So I want implement event handler for game. All right. So we want the update here, as it were. And inside of update, I want to run a loop essentially, and I want to control how often we're running this update. So maybe before I do this, let's switch over to my brand new whiteboard scene, which I unfortunately do have to walk in front of, but the audio should be, yeah, the audio is working for that. So let's imagine that we have this line, this timeline. And right now, we're running these renders as fast as possible. So they're sort of running like this. And so we'll put like a render. So like down here, these are renders. Updates are happening at the exact same frequency. So we're just running them at the same rate that we're running the renders. So we have update. I don't know how to spell update apparently. Updates. And renders. So what I want to do now is make it so that the updates happen consistently regardless of how many of these we have. So GGEZ actually gives us something like this. It's a lag counter. Specifically, what I want to do, and maybe before I leave away from this, what I want to do is convert these from just running at the same time. I want to now divorce it from the render timing, and I want it now to run at something very even cadence, like this. So let's say this is something like 60 FPS, but maybe the frames per second is not exactly right. I just want the equivalent of 60 frames per second run the update loop, while the graphics can render as fast as machinely possible. So let's implement this first. And back to main. All right, so here we are in update. The way we're going to do that is we're going to run an inner loop inside of here. So while timer, so timer actually gives us this for free. It's this check update time here. Check whether or not the desired amount of time has elapsed since the last frame. This function will turn true if the time since the last update call is equal or greater to the update frames per second indicated by the target frame per second. So let's go ahead and implement this. So timer, check update time, hand it the context, and then our target frames per second. So we could set this to 60. We could also use it's probably better to use a constant for this, which we will in a second. And I'm going to wrap the entire update method inside of here. So save you. I feel like it put the closing one inside of match. Is that right? Yeah, here's the while one. That was, yeah, okay, now it's bad. Cold folding was a little bit weird with that one. But now, if I run the game in normal mode, it's still going to render as fast as possible. But the game is actually running what looks like very slow here. Bring over this again so we can see. We have maybe saved a little bit of CPU, and we've saved not really much in GPU. It's still about the same there. However, the game is much slower. This is based upon 60 frames per second for update, whereas the display, I'm getting 156 frames per second. All right, let's try this again with release mode. We're getting 2,300 frames per second still, but notice that the game is running at what appears to be 60 frames per second. So we have successfully limited the gameplay and made it consistent across, well, different CPU and GPU speeds. So if I now package this binary up, hand it to somebody else whose computer can't run this fast, then they're going to get the exact same experience of playing it that I do. The obstacles will still move over just in this speed. The trees will move in this speed. and the jump happens in exactly the speed. The other thing is, like, my jump is sort of not consistent. This is going to make it so that I can, well, I know exactly what the update speed is. I no longer have to do anything weird like passing in delta time or anything else to try to make the jump consistent. I now can just, I know that it's going to be based upon 60 FPS for the updates. And maybe we should change that. Maybe it shouldn't be FPS. Maybe we should change this to UPS for like updates per second. Because now we have two numbers. We have updates and renders that are separate from each other. Let's go ahead and make this into a constant here. So we have this, we're not using it right now. Let me change this to updates per tick. It's a U32 because that's what's required down here. And we're going to make this 1000 divided by 60. So that's our target goal here. I actually should make this just 60. Because here, that's what it's expecting, this full U32 number. So updates per tick. So save that. This should still work the way we're expecting it to. All right. So the next thing we want to do for this entire limiting like the frame rate or like making sure the frame rate is fine is now we want to be nice to our computer. Notice that we were getting like 70% GPU usage out of that. My fans were spinning up. I don't think you could hear that on the microphone, but it's pretty annoying that this simple game, like for those elements that we have on a screen, is using that many resources. And the reason it's doing so is because it has to draw like 2,300 times per second. Let's limit the draw updates now. So that's going to come back down here to this loop that we have. So I discovered the problem yesterday. It's kind of hilarious. I put my start here before the loop. Not good. We need to, we need to start here. So we're going to do let start time equals, and this is going to be timer. We want this to be a duration, an instant now. So let's do standard time instant, and I think now. So that gives us the start time. And then at the end of this loop, after the draw, we want to now get the end time. Okay, so now we have the start time and the end time, which means we can now calculate what the, how long, like the duration of this, of the entire frame, this tick took. Now we got instants. I don't think we can subtract instants from between each other, but we can convert these to durations, which we can definitely do. So let's just do dot, I know elapsed turns the amount of time elapsed since this instant was created. Actually, that sounds like we don't need to use this one at all. Let's just do let elapsed, like maybe tick time elapsed equals start time dot elapsed. So this is going to be a duration that is how long this loop, this individual tick took. Okay, so there's that. Then we have our target, like how long we want this to last. If we are below that, so if we have time left over, then we're going to want to do some math based upon this. So the general idea here is going to be, let's do this in a comment. If tick time elapsed is less than target draw FPS. So we have UPS, which is our updates per second. This will be our frames per second, the actual drawing out. So if we're less than that, then we have time to spare and we want to pause ourselves before continuing on. Then pause for like whatever the remainder, whatever the difference is, to make sure that we get up to our target frames per second. Difference between target and elapsed time. All right, so we can, if we have the target draw FPS, which is just going to be a number or a duration, so that means we need to create a duration for what is it that our target is. Const, this is going to be updates per, not updates per frame, this is going to be frames per second, target, which is going to be a type duration. So standard, I can actually, we use duration enough. I could bring it in. Go ahead and use standard time duration. So you are going to be a type duration, and we're going to set you equal to duration from milliseconds. So we'll just do all this calculation in milliseconds because that's a little bit more precise. I don't think I need to go into nanoseconds for this. So we're going to start with 1,000 is 1 second, divided by whatever like the draw update, the draw frames per second target we're going for. Let's aim for maybe like 144 or so. We could even aim for 90, as long as it's more than the updates per tick. That's fine. This is going to be our being nice to people who have better systems. They're going to get a little bit smoother animations. And that's it. The updates, however, are going to be the same regardless of what computer you have. So if you can only draw like 20 times per second, it'll still play at the same speed, and you can still predict when to jump based upon that. So let's go ahead and use our frames per second now. So down here, durations are actually, we can use all the math and everything else based upon them. So if our elapsed time is less than, so this is going to be tick time elapsed, is that if that is now less than our what is it, frames per second target. So if that's less than that, then we now want to sleep. So pause for the difference between the target and the elapsed time. Otherwise, we do nothing at all. So we know how to sleep. We actually have, like, GGEZ gives us that off of the timer. So we're going to need to figure out how to calculate this, which is pretty simple. Durations, we can subtract from them and then get the result out of it. So we can have let sleep time equals, so we know that the larger number here is going to be the frames per second target. So we'll just do the frames per second target subtracted from the tick time elapsed. This is going to give us a duration here. which is sleep time. Okay, now we need to actually call the sleep, command. So this is gonna be timer and sleep, and then we pass it the duration, which is sleep time. This should now pause and halt the this entire frame, the drawing frame, until it's done. Now this pauses both update and draw, this is the reason why it's important that this number be larger than the updates per tick we want. So in a sense, we now have two loops going on. We have the drawing frames per second, and we have the updates per second. So if we save that, let's go ahead, let's run this and see what happens to, well, our game. So cargo run. The game plays around the same. Did I not do it? It's not limiting us. None of that has changed, I think. Let's make sure that this is working correctly. I'm guessing it's not, because this sleep time. Let's do a debug on our sleep time and like figure out what that should be. Debug sleep time. We'll need to, oh, no, you're just fine with that. I keep on forgetting which one takes ownership and which one does not. Okay, so we're getting no console logs from this. Or that's JavaScript. We're getting no debug logs from this. So therefore, this isn't actually running. So tick time elapsed. We need to figure out, is this actually turns amount of time elapsed since this instant was created, which should be here at the beginning of the loop, like inside the loop. Let's figure out tick time elapsed. Let's see what this is. Oh, that's not running at all. Did I not set it to run this loop? Let's go take a look at main. Oh yeah, I may have been a little bit too overzealous in my sort of resetting. I forgot that I'm not running this run. Okay, so instead of matching event run, we're going to match. Let's see, where is it? GG Infinite Runner, my game, and we're gonna add in run here. And so here we're just gonna straight up run like that. Now we're gonna run that custom loop that we created in the library file. And here we are limiting our frames. It's actually slightly less than what we were going for initially, but the game speed is the same as when we had our when we weren't limiting it. So part of the reason why it's not exactly like perfect is the thread sleep that we're doing, like the pause. That's not perfect. It's not actually going to every single time sleep for exactly how long we want. Sometimes it sleeps for a little bit more. Sometimes it sleeps for a little bit less. Looks like it's generally a little bit more. However, if we take a look, okay, so we have our time elapsed that's going out here. Let's remove that. Let's remove that debug run. So we're not taking up any extra time. And let's show off what our new resource consumption is. So we are at 5.4 around 5% CPU speed. That's a little bit less. And we're at 7.5 GPU, which is significantly less. Now I know that just like the normal version of this, that was fine. Also, we're at FPS 150. It's staying lower than before. What did we say at our 144? Now, if we remove this down and we make this like 90 frames per second, we should see that update in how long it takes. So you notice that the frames per second takes a much longer to spin up, as it were, and it's stuck at around 83. Now this is also an average over the last 200 frames. That's why you see it sort of like go up slowly. It was, you know, close to 90 from the beginning, but of course the first frame was 0, so that affects the average quite a bit. And the speed is exactly the same. So now let's run this in release mode. And we'll have the task manager open so we can see what this looks like here. Game runs at the exact same speed, and we're still stuck to around the 83. So we've actually slowed it from like 2,500 frames down to 83, which is super, super nice. And that shows here. We're using 0.1% of the CPU and 4.7% of the GPU. This is significant savings. I could now potentially run this along with like several other games at the same time if I needed to for, you know, any kind of reasons. Like if I wanted to have this up in the background just running, it's not going to cause my fans to go crazy. And it's not also, it's now we've switched to very low power usage. So if somebody has a notebook, I'm not going to like suck up all their power within 5 minutes. The real benefit though is now I can fit more trees on the screen. I can add clouds, I can add other particle effects, I can add more obstacles, I can add way more stuff. We have a lot of CPU and GPU to spare at this point in time. But we have a problem. So we're not done yet. The problem we have now is, and I don't know if you can see it, it's kind of jagged, the way that everything is moving. We're not getting very smooth runs here. And looking at the preview, I'm not sure it's completely coming across, but let's go back to our whiteboard and I'll sort of explain what's going on here. So we've successfully switched this up. Now it's, you know, we have made it so that the renders are happening less often. Yes, that's true. So we have something like this now. But with the updates happening only on this sort of set time frame and the renders happening more often, and then 60 to 90, that means it's going to be one render per. So let me make this actually a little more realistic here. If we start right away, right there, but then we're going to have another render, like maybe right here, and right here, here. It's actually a little bit more than the updates. So it's probably something like this. So for every one update, we have 2 renders. The problem is because we're updating, when this render, the first one is fine. The second render right here, it says, hey, give me the position of the obstacle. So let's draw the obstacle out here. So give me the position of the obstacle. That's where it starts right here. Now this update that happens right here, that's going to move the obstacle, let's say, it wants to move to this position from this update. However, this render is right before the update, meaning that it's going to draw it in this position still. So for 2 frames that we can see, it'll be drawn here. Then the update happens, and suddenly it pops over here. But then this next update happens, and it stays here. Then the update happens, and the position gets updated here, and then suddenly the next frame is over there. That causes a little bit of jumpiness for us. So we're not getting super smooth graphics. So we can fix that. What we need to do is we need to figure out where we are within the entire update render, like where our render is compared to the updates, percentage-wise. And then we don't update, like we don't actually update the location, but we can fudge the numbers and have render basically say, well, you're actually over in this area. So let's draw you in a different place. So let's take a look at that for the obstacles first. So what does that mean for us? Let's go into the obstacles here. We have this get location. This get location is being used by the draw method that we have in the main library. And it's getting this in order to figure out like where to place it. If I update this get location to maybe like an offset percentage, so offset percentage, and this will be an F32. Now, what I can say is the Y location will never change for the obstacle, so I don't need to calculate that. But the X position does, and we know that's always moving to the left. This is going to be really simple. We're going to say that we want to subtract from this, move it more to the left by the percentage that it's between the update, specifically between the update line and the render line. So for that first one, we want to, what is that, like 80% or so? We're going to have to move 80% further along than what it has right here. Well, but we're going to have that offset percentage here. So let's go ahead and we're going to say, we know the velocity. So it's going to be self.velocity.x times the offset percentage. And this will happen first, and then it will subtract from this. So that should make it very smooth. It's kind of what our eyes are doing. It's predicting where it's going to be based upon the last time that we actually took a sample of where it actually is. All right, that should be it for our change to the obstacle. We now need to actually do that calculation in draw here. So if we take a look in draw, we have match game state, when we're playing, draw the 2 obstacles. We now need to get that percentage. Okay, so we actually can get that percentage here. So we're gonna let, this is, well, let's take a look at what we have here. So it's timer. So the remaining update time returns the fractional amount of a frame not consumed by check update time. So this will return like the number of milliseconds is the remainder. So let's see, our updates are 60 milliseconds and the draw is 90 milliseconds. That means we could potentially have, you know, let's see, what would that be? 60 frames per second would be around 0.16 666. I think so. No, it would be 16.6666 repeating milliseconds. 90 would be 1.5 times more than that. So like what, 11 milliseconds, 10 milliseconds or so. So that means anywhere between 0 and like 5 or so, the difference between those is what we might get out of this. So let's do the let updates per second difference equals, then we have our timer, and let's just get the remaining update time, pass in the context. And so this is going to be a duration. So we're probably going to want to convert this to a, because we have here this updates per tick, that's a U32. So we're going to need to pass in like an F32, we need a percentage, meaning that we need to take this number and divide it by this number to get a percentage of that. Okay, so I guess if I change this to be percentage, so what does that mean? Well, first of all, we need to convert U to be into milliseconds. As milliseconds. Now, what is that? Oh, that's a U128. So that's unfortunate. We're probably going to want to convert that to a U32. So as U32, okay, that's now a U32, and then we're going to divide by this updates per tick. And that should give us a percentage. Now, there's another problem, which is this will always be 0 because U32s can't, like, these are just integers, 1, 2, 3, 4. We should probably actually convert this to an F32 and convert this to an F32 as well. Now I'm going to have a fractional number between 0 and 1. A percentage, as it were. So then I can now hand this to our get location. Let's do them to both of them at the same time. We're going to hand the updates per second percentage. So if I save this and we rerun our game, what error do I have? Oh, yeah, I noticed that my get location is actually being used in running into an obstacle as well. Well, here I want to make sure that our offset percentage is 0, which won't change the location at all. It'll remain the same. No errors anymore. Let's go ahead and run this. So now we shouldn't get the weird jittering that we have. If it's still like not super smooth, that might be just like the numbers are slightly wrong. But now it's calculating what those differences between the updates and the renders are, and sort of moving the obstacles and like displaying them in the appropriate spot. And I think I get a significantly better view out of this if I use not 90 frames per second, but if we go up to like 144. Then it's nice and smooth like this. So then we want to do the same thing to the trees. That's the only other thing. And then maybe we can fix the player when the player jumps to be consistent. So trees. We need the tree. It's going to have its own get location, I bet. Or no, we have its own draw here. Okay, so it's params destination 0.2. So here we need to get this draw tree model RNG. We're also going to need to get the sort of like the difference, like the percentage offset. So percentage offset, which is going to be a F32. And now we can do exactly the same thing. We don't need to worry about the Y. We're just going to worry about the X here. So minus, it's going to be our percentage offset times self dot, do we not have a velocity? We have a location and we have a tree type. Where is our... Oh, I think the velocities are based upon the tree type. Where is that? Oh, we'll need to do this this also here. Update. Oh, okay, so we can get the velocity here. So tree model.get velocity. Pass it in the tree type, and that will let us know what we need to do here. So this is going to be self dot tree type dot tree model. Oh, it's not self. We are getting passed in the tree model. So tree model dot get velocity. Pass it in self dot tree type. So then we really care about the X here, and we're going to multiply that. And we're going to do the exact same thing to here, to the leaf count. So the destination self dot location dot X minus. Save that. Expected a reference to that. Let's change that too. For arguments. Right, so now wherever we call the draw for the tree, so here that is, we also need to pass in this, this sort of like percentage difference. So let's add that in here. So the offset percentage, which we know is an F32, we can then pass that in here. Okay, so that should make the tree draw happy. But now here, draw trees, we're then gonna pass in updates per second percentage. And no more errors. Let's go ahead and run this again. We've got super smooth obstacles that are coming along, and let's wait to see if the trees show up. And there we go, the trees are coming in too. The trunks are where we get to really see that sort of like the weird shifting back and forth. And there's a tiny amount, I don't think it's exactly the same that it was before. Was there like a trunk also that I have to do? The branches look great. I don't remember if there was like multiple draws. Looks like there's only two. There's the, oh, okay, this is the trunk mesh. So we did the trunk and we did the branches. So it's never going to be perfect, but we're always going to get, like, we're going to get a lot closer based upon this. The other thing is that if we have like fractional pixels, it's like not going to necessarily sure how to draw those out. But that's it. That's now limiting the frames per second, making it nicer in our CPU and a computer, limiting the amount of power consumption, and making it so we're going to be able to draw way, way more stuff onto the screen at the same time. So let's go ahead and take care of all of these warnings here that we no longer need to worry about. And then I'll push this code up so we can all play around with it. So game state, variance is never constructed. Our game state, I think we don't need you then. We're not using you. What do you mean you're not constructed if we're clearly using you? Let's go back to, where was that? Wasn't there. Where was our game state? enum game state. It's on our player. Was it this? No, it wasn't the possible observer. Okay, so what are you upset about? Possible observer game state. Wrap to game state. So possible observer. Let's go here. Okay, so I mean, just because you're not constructed doesn't mean we're not setting you. Let's remove the, let's derive born dead code. Oh, there's a way for me to turn that off, isn't there? And I can't remember off the top of my head how to do that. Let me go ahead and push this code up before I do these changes. That way we have a working version. But if any of you have any questions, please ask right now, and then I'll be happy to sort of answer them as I can about this, about the game loop and making the graphics smooth, and also not making the fans go up for, you know, by everything. So learning game design patterns, stage all these changes, limiting the updates per second and frames per second. And I'll push that on up. The code you can find with the command bang repo. And that's a link to the code that I just pushed up. And I'll also have this code in the description of the videos. All right, back to you. So game state is never created, huh? Which means that we kind of don't need it. But if I take this out, we're checking for it everywhere because we're good Rust citizens. So if I just do that, let's see all the places it breaks. So the player mod, if that possible observer game state wrap game event. So this can't happen anymore. So if I take you out, oh wait, I think let's make sure that the game is working the way we want it to work to begin with before I start doing this, because I think I took away in main here. When I create, I'm not adding the observer. So we need to do that. And so then, so possible observer, so there we're gonna make you work again. There we go, this should, okay, and then the game should now work as expected. So we can just go normal run mode now. we can jump over. We can jump over the obstacles, we get a score, and if I get hit by an obstacle, it ends the game. Okay, and then we can start over again. Perfect. So that reduced our warnings by quite a bit. Okay, so field is never read, target FPS. So yes, we're not using this target FPS anymore. Let's go ahead and get rid of you. Which means this is no longer needed. Save you. And in main RS, we're using our own game loop, so we don't need event anymore. And that's it. No more errors, no more warnings. Everything is just fine. So we could run this again as a quick test. We can put in release mode this time. And the game is playable as it is. The other thing this allows us to do is make sure that our jump is consistent, because sometimes we get that sort of really like crappy low jump, and I don't know about you, that would piss me off if I go like I have a nice high score and then I go to jump and I like jump like 2 pixels. So let's make our jump consistent. So first let's get commit message would be removed warnings. Okay, so jump. In the player, we have, player data is separate. So let's go to the player data here. Here's our jump force. Chantilly, good morning. Here is our jump force. Okay, so we're setting that to -7. That should be fine. Then I want to, did I get the timing working? I did. It is working just fine. So let's go to where we're implementing the player. So where are we doing the jump? We have apply force. So acceleration plus the force, that's fine. We have run here. Okay, so player states jumping, self dot apply force, jump force. Okay, so that seems all fine there. Mr. Halsey, good morning. Where is anything that would cause hit the ground? This all is all fine. In our main, are we doing anything with like delta time? Because like that's usually where I've noticed that problems come in. Let's take a look at update inside of here. So we have the event handler, we have update. So while we're playing, okay, so we apply gravity. We hand the player the command that they're running and the arena height. Have them hit the ground with the arena height. We run, obstacle, time since start. Oh, and then we increase the speed. Good to see Rust programming. Yeah, no, I really enjoy Rust. So I'm planning on continuing to stream and record these videos. Update trees, create tree. Okay, so this all is fine. Why is it because it has to overcome the gravity, and like that's not consistently affecting the player? So if we do player, so we're always affecting the So we're always doing this. We're always affecting gravity with the player. And if we go back into our mods player, here's this apply force. This always sort of takes into effect with this. In run here, we match self.state. Oh, I think I know what's gonna be the problem here. When we're jumping, so jumping self apply force in air, we apply this. This is the only time that we apply our acceleration. So while we're in the air, it's fine to see our gravity sort of pulling our player down. But because we're applying gravity when they're not in there, that the acceleration is just building up to be like extremely strong and like pulling that character down, even though we're not applying the physics to it. So we're not resetting the acceleration every single update frame. So what we need to do is in the air, this is the only time that we're going to apply the gravity. So let's have the gravity be passed in here. So we're going to have gravity, which is going to be a vector 2 of F32s. And so in the air, we have our velocity. Let's go ahead and also do self dot player data dot, actually it's going to be self dot apply force, and we pass in the gravity. So we're going to do that here. Then we reset this acceleration, and then that way it only happens at this point in time. So we're going to come back to the main library. It's going to say, hey, why are you attempting to do this now? You need to hand in the gravity. So self.gravity comes in here, which means that this apply force no longer needs to happen. So if I rerun this, now my jump is consistent every single time. So in previous games, I was always messing with delta time, trying to make like the animations consistent. I was doing all sorts of tricks like that, and they never really worked that well. But this is such a better way to predict exactly what the numbers we need to have. Like if we know that it's always going to be 60 updates per second, then the numbers are really easy to sort of fudge or work with. We could even have like the draws happen at 60 frames per second, but the updates happen at like 30 frames per second. There's so many different things that we can do for this. And then that's how we can fudge the numbers to make it so that we it works really well with whatever speed computer we're working with. And that's it. So now our player jumps consistently. So that is another bug. Smashed. So player now jumps the same height every time. And I'll go ahead and push those changes up. And with that, it is 8 o'clock. You see that the frames per second go between 120 and 150. Yeah, it is a it's generally, I don't think it's going above 140 or so, but let's take a look. That counter is an average counter, so it's not like a real frames per second counter. It's not perfect. So it may actually be like slightly wrong sometimes. But yeah, it looks like it's staying around like 140 or so. Comes here, it drops a bunch because I'm doing a little bit too many draws for this. You know, and this is really interesting. I could dynamically change how many times we're doing like the updates or the frame per second draws just based upon what state we're in. So that would be super interesting too, to like update those variables. But yeah, I think it's I'm telling it to stay around 144. The average might, like, it's not perfect. That sleep timer will sometimes go over, sometimes go a little bit less. So it's not like I'm not perfectly set to 144, but it's trying to be around that. And of course, it'll be less when it just can't keep up for some reason. But as long as it's above the updates, then as a player, you're not going to see any problems. The trees are tearing. Oh man, okay, I thought I had fixed that. Not the triangles, just the trunks. Okay, let's make sure that I did the trees properly here. Because I do tree model get velocity, handed the tree type dot x, and multiply that by the percentage offset, and then that's where we're going to draw them. And so I think that's where I want to go. If we take a look at the tree model, there's only one get velocity here based upon the tree type. It's just going to be whichever velocity it is that we have. Now, I wonder if we change these to be closer to like even numbers. Like if I make the velocity of this like -1, and this one like -2.0, will that make the tearing a little bit better? This one, that sort of looked like it's more of developer mode versus release mode problems. Let me do this in release mode. I know that in release mode, it everything runs a little bit smoother. It's adding in a lot of problems. Okay, so I'm seeing a little bit less. I think that's better. So if I was to do this, I would need way more trees. Because now the trees are moving too fast, you don't get a forest effect. But now that we're using less resources, we can totally do that. We should be able to add in, where do we create trees? So an update. We have create tree here. We have current, time, index. We're cloning the tree from there. Okay, so create tree, so between 1 and 15. So let's make this like 1 and 5. So three times more often. Yeah, and I also read before that there's a lot of games for like little tiny problems with tearing that you can't get rid of through making the game loop better. You can use what is it called? You can use motion blurring to fix that problem. So in motion blurring, we could definitely say, okay, now we blur the edges of like where the next frame and the previous frame is. It's a little bit more calculation work, but it will hide any kind of tearing, residual tearing that we can't get rid of. But I know that some people can't stand motion blur, or it might make you like feel sick. That's definitely a consideration. But it's looking good. The game is definitely looking good. It's fully playable. I have to actually jump over these if I want the game to continue on. The forests are actually looking really good with this. And if we take a look at that was the wrong one. Ooh. Oh, that's a weird bug. I moved away and my player is gone. Well, now it just runs forever. We're still at 0.1 CPU and 11.6. So by making the trees 3 times more likely to happen, we increased our GPU by like 2 times, which isn't terrible. But that was a weird bug, and I'm not sure how to recreate that. The player's just gone now, so that's cool. It'd be nice to have the trees have its own outline at the green part. Oh, you know what? It would be better to have like different shades of color for each tree. Which I think that we could easily do also, is to, for the tree model, is it the tree model here? Yeah, we have this like branch color, and we have the leaf color. Yeah, the branch color. So we could have the branch colors be different, and we could have the trunk colors be like just ever so subtly different from each other. That would be good too. Random green shades. Yeah, definitely. That would be really nice. This tree model is what's being used to sort of replicate from. So we'd want to remove it from the tree model and put that on the tree itself. So that way when we do the color, our draw params, we could then set a destination, and we can also set a color based upon this. Which I don't think that would be too hard to do. This is a new... Oh, you know what it is? Is because like the trees, we have trees created like this, and in our main library. So we'd need to redo the way we spawn the trees. We create a tree in new here. And we have a vector of like trees to clone, which I guess like that's a little bit unfortunate. So we actually create the tree at this point, and then we just clone that tree over and over and over again. That's not necessarily what we want for this. We're probably gonna want to. Well, if I could do this all over again, I would probably not use the trees to clone. We're just sort of doing that to show off the prototype, a sort of design pattern in this code. It's not like, it won't allow us to customize the trees now, so we're locked into place. So I don't think the prototype was maybe quite good for that, or we have to create a whole bunch more types of trees. I could definitely say like tall trees get this, and short trees get this, you know, the other things. We do tree model. So tall trunk, and so here's this. So tall trunk mesh gets this color. So in mesh builder, new. So if we pull in RNG into here, then we can set the random tree trunks. So if we're gonna need use rand I can't remember what it is. I thought it was like threads, like thread range is the type. Oh, thread RNG. Is it prelude? Wherever thread RNG comes from in there. And then when we create a new tree model, we need a RNG, which is a reference to a thread RNG. And so then here's our rectangle. So trunk mesh, tall trunk mesh, leaves mesh. Oh, I don't have the leaves mesh are the same regardless of which type you are. So I would need a tall leaves mesh and just a leaves mesh and add that in. Okay, so I'm not gonna finish this right now or do this right now. That is, I think, something that I'll leave for everyone else to sort of work with this. It's gonna be a little bit more of a refactor than I would like to do for the time that we have remaining. So next time we're gonna move on to the next chapter because we're done with this here. And the next chapter is going to be the update method. So it'll be interesting to sort of to look through that. But with that, I'm going to go ahead and get ready for my stand-up meeting for the day. Is there? Yep, I got everything sort of set up for this. So everyone, thank you so much for stopping by and watching. I hope that going through the game loop was really helpful and us sort of like now normalizing what our updates per second are and our drawing per second are. And now we can make it so we can update the drawing per second and not update the updates per second. So everything just works and is smooth and is nice. I've got the code up there. I'm doing these streams every single weekday morning at around 7 a.m. Mountain Time. And you can follow me here on Twitch or on Twitter for notifications for when I go live. With that, I'm going to switch over to the ending screen. Have a great day, and I will see you next time. Have a good day too, Chantilly.